So in the meantime, if you want, I'd love to hear more about Landscape.
Yeah, sure. I think we can just do a quick round of intros with everyone so that I'm not sure if everyone here has met you before, but yeah, I mean, we already have met, so I'll let others start that so we can go alphabetically. Alex, Ajay, Bharat, Himanshu, and Saurav. Alex, do you want to introduce
Yeah,
yourself?
sorry, my microphone wasn't happening. Hi, my name is Alex. I'm currently a MN student at MIT. I am going to be studying program synthesis. I don't know if you know that area, but I'm going to be with Armando Solar-Lezama, who works on neurosymbolic synthesis.
Cool. Ajay, you want to go next? Okay, we can't really hear Ajay. But just a quick heads up, we are live on the Slack.
Oh, okay, great. And yeah, I'm very sorry for the scheduling issue in the previous talk. So I'm real sorry about that. Thanks for having me back despite that.
Yeah, no worries. All right, we'll just do the intros again. So Bharat, if you want to go next, and Himanshu and Sarika.
Yeah, sure. So myself, Bharat, I'm a senior undergrad at IIT Delhi from India. I basically work on adversarial robustness of the graph neural networks and neural and differential neural architecture search for object detection. Those two things I'm currently working on.
Hey Michelle, I'm Himanshu. I did my master's at Miller and I'm currently a machine learning engineer at Workday. And I'm usually interested in NLP and optimization.
Hi Mitchell, I'm Saurav. I'm currently stuck in a limbo between high school and college, but I work as a growth machine learning engineer at Weights and Pisces. I'm pretty active on Kaggle, and I'm interested in the theoretical foundations of deep learning. Nice to meet you.
So I guess we can get started. We Ajay will have some time to introduce himself towards the end, I believe. But we are live, I can see. So yeah, let's start this. So I'll just do a quick intro. So hey everyone, this is the second episode of the Landscape paper series, and for this time we have Mitchell Wortsman. I hope I'm pronouncing your name correctly. He's a PhD student at University of Washington, working with Professor Ali Farhadi, and I believe everyone knows Professor Ali Farhadi from his works on Yellow, I believe. And I met Mitchell. I believe I met him first in a talk at Roseanne's annual DLCT series where you presented Supermasks and Superposition, I believe. So I came to know about your works over there, and and then we met at ICML for your paper on learning neural network subspaces. So I believe those are the two papers for your presentation today, and you also mentioned that you had some new results that you wanted to share. So yeah, stage is yours.
Yeah, okay, thanks so much. I will turn off my video probably during the presentation because it seems that I can't see. I cannot do this and share my screen. But yeah, thanks so much everyone for having me today and for coming. Very excited to be here and share research and yeah, I'm looking forward to discussions and like this. Let's make this sort of as informal and discussion based as possible. So just at any point, just interrupt me, just jump in. Yeah. Okay, so I assume everyone can see my screen unless I hear otherwise, and that everything's good and I'm not on mute. That does seem to be the case. Okay, So today we're going to talk about neural network subnetworks and subspaces. This is sort of some research that I've done with some collaborators over the past year, 2 years or so, and I'm excited to hear people's thoughts and what they think. Yeah. So part one of this talk is going to be focused on subnetworks, and we're going to begin by just sort of covering, well, you know, we know about neural networks, but what do we mean when we say subnetworks? And really, this research sort of started by looking at the lottery ticket hypothesis by Jonathan Frankel and Michael Carbon. And I assume people here are mainly familiar with this really interesting piece of research, but I'll cover it again just in case not. So what the lottery ticket hypothesis says is that, well, we have this neural network over here, and then what we usually do is we train, let's see, I wonder if people can see my cursor. I hope so. Let's check. Yep. Maybe not. Oh yeah, okay, great. So we have this neural network over here, and then what we do is we train, and then we get this neural network over here, and here colors denote sort of this change in the weights over training. And what the lottery ticket hypothesis says is, well, actually, there's a sparse subnetwork of this neural network. There's a sparse subnetwork, and if we just train that sparse subnetwork, we're going to get a neural network that actually achieves similar accuracy to training all these weights. And here we see that we're sort of denoting a subnetwork by actually with a binary mask M. So a subnetwork is expressed as a element-wise product between a binary mask M and a set of weights. So, okay, knowing that, we're going to talk about some really cool follow-up work by Joe et al. Oh, sorry, here's sort of the kind of formal expression of what the lottery ticket hypothesis actually is. And I really recommend you read this paper if you haven't seen it. Okay, so now we're going to talk.
I had a question.
Yes.
So this question is not necessarily related to the lottery ticket hypothesis, but this is something that has been bugging me in relation to that. So the hypothesis states that there exists a sparse subnetwork within the main dense network that can reach the same accuracy if initialized and trained to the same number of iterations. But is there any conclusive evidence or proof that states how many unique subnetworks exist for a given dense network with a target sparsity?
So that's a very good question. No, and I think that there's not even really a consensus of if this is true for larger scale problems like ImageNet, but this is definitely true and verified for recognition problems with like SciFar. My guess is that there's a ton of subnetworks. It's not just specific to one subnetwork. I think that there's probably been work in that direction, but unfortunately, I'm not can't remember anything off the top of my head. But yeah, basically, my impression is it's not just one subnetwork; it's many.
Great, thanks.
But this is sort of the hypothesis, and then so follow-up work that was really interesting by Joe et al. Said, well, do you actually need this training step here? What actually happens if I just find a really good M and don't do any training at all? And that's what Joe et al. did. They said, well, let's consider something called the supermask. And a supermask is just a mask that I applied to this random initialization, and I'm going to get a neural network that performs very well. So surprisingly well, much better than random chance. And for me, when I first saw this result, I was pretty surprised because you think that like all of the sort of juices in training the weights, and Joe et al. Showed like, no, there's these things called supermasks. With some co-authors, we took this result a little bit further and showed that actually with kind of minor improvements to their algorithm, you can make these supermasks so good that they can actually reach the similar accuracy as actually training a neural network, which again we thought was a really nice result. So basically the takeaway is from these works is that pruning is learning, and so this is sort of what we're going to now use to develop this notion of supermasks in superposition. Okay, great. Any more questions on the context before I proceed? Okay, great. So basically now we know what supermasks are. They're sort of when we just overlay binary, we just prune some weights instead of actually training some weights. But what should we do? So what? So basically, here's kind of the takeaway. It's that a neural network can only have one set of weights, but a neural network can have countless subnetworks. What we can do is actually we can therefore sequentially train a single network on thousands of tasks without catastrophic forgetting. And we can do so by, for each new task, let's just sort of learn a new subnetwork. And they're all going to sort of live inside the same network, but they're each going to be sort of a different subnetwork. So this is kind of the main intuition behind this work, is that a neural network can have only one set of weights, but countless subnetworks. So here's actually the picture that we have in mind here. So it's just it's like there's a helpful mnemonic, which is like new task, new mask. So keep the underlying weights fixed and random. So never allow the actual weights to change. And then for each new task that you see, so task 1, task 2, task 3, we're just going to learn a new binary mask M here. So that's supermasks and superposition, at least at a high level. I hope this picture makes sense to everyone. And if there's any questions, please ask.
Yeah. So for these n tasks, are you generating masks which are dependent on the complexity of the task, or are they just all homogeneous, unique masks?
So this is a great question. For this paper, we're just considering tasks which have sort of similar complexity as each other. So we don't actually have to think about that, but extensions to kind of tasks with different kind of varied difficulty and using budgets accordingly would be really interesting. But that's a great question. Okay, so yeah, sorry.
Yeah, I have two really quick questions. One, is there any overlap between these masks for different tasks? I'd assume that you could probably share some weights for similar-ish tasks, right?
Yes, there is overlap, and we've tried to, I think, capture this a little bit here. Like you can see this one has some overlap here, but yeah, that's a great question. There is overlap.
I see. Okay, and the other one was, is there like any specific algorithm you use for deciding how to lay out this mask, or is it just random?
So basically, the mask is just learned in the same algorithm that we used here. And we can talk about that. The algorithm, I think, is not actually so like too important, but just pretend there's an algorithm for masks. And then at the end, if you want, we can spend some time talking about what that is. But yeah.
Okay.
Okay. Basically, the algorithm uses a straight through estimator. It assigns a score to each of these weights in the network. And basically, if the score is high, it's included. It's a 1 in the mask. If the score is low, it's a 0 in the mask. And you can just sort of backpop through the whole thing. Yeah. Okay. So let's talk about a little bit about how this performs. So first, we're going to look at the performance on a task called split ImageNet. So you take ImageNet, which is a 1,000-way image classification problem, and then we're going to split it into 100 different 10-way classification problems. And you're going to learn each sequentially. So first, I'm going to train on 10 dogs, or sorry, whatever it is. Then I'm going to train on 10 fish, whatever it is, and keep going and keep going. And now you'll notice that if you just take a normal neural network and do this, okay, sure, it can learn dogs. But then as soon as you start training on fish, the weights are going to move and it's going to forget everything it knows about dogs. This is called catastrophic forgetting, and this is exactly what we want to avoid. What we hope to avoid with supermasks and superposition, because it's sort of almost a hack. We no longer have this catastrophic forgetting issue because we just don't allow the weights to change. So the upper bound here is just training a different ResNet 50 on each of these 10-way classification problems. And this gets an average accuracy of around 92.5. But it uses a lot of bytes because it's going to be training a different neural network, a different set of weights for each of these tasks. So there's this baseline called batch ensembles, which is a really interesting method. And they can do things really efficient, but basically accuracy isn't as high as we might like. So supermasks and superposition, which we're going to call SUP for short, actually allows us to get much better accuracy while still sort of using a reasonable amount of bytes. So here, 100 megabytes. And essentially, we can get different accuracies here by just varying how sparse we allow these masks to be. So if the masks are very sparse, and remember these are binary masks also, so they can be encoded really efficiently. So if we make the masks really sparse, we can use 65 bytes. So we can do 100 different tasks with less bytes than a single ResNet 50, which is really cool. Oh yeah, and it's basically we can use less bytes than a single ResNet 50 because we're never storing the underlying weights. All we have to do is store the random seed that was used to generate those weights. So this is sort of to me this result was the coolest from our paper, but we'll continue to talk about others. But does that make sense? Sort of that you can vary the mask sparsity and you get different kind of amounts of bytes for solving this problem.
Yeah, I have a question about, just to clarify.
Sure.
So you're using the exact same set of weights throughout the entire procedure, and the only thing that's changing is like the masks?
Yes, exactly. So if you look at this picture, this data, these are sort of the weights of the neural network. And the only thing that's changing here is for task 1, we'll use M1. For task 2, we're going to learn M2. For task 3, we're going to learn and use M3.
I see. So what is F here then?
F is sort of a neural network. So the neural network takes in two things. It takes in data, and it takes in parameters. So X is the data, and this is sort of the parameters of the neural network, if that makes any sense. So essentially what we're going to do is we're going to take these parameters, and we're going to selectively turn some on, and the rest are going to be 0.
Okay, so how are the weights initialized at
randomly.
the start then?
The weights are going to be just initialized completely randomly.
Just random. Okay.
Yes.
So like normal, or like does it matter how they're initialized? Because I imagine like some initializations would lead to better like subnetworks, right?
That's a great question. Yes, we're using K-Ming normal initialization, and that does matter.
Okay, cool. Thanks.
Okay. So great questions. Okay. So yes, let's proceed. So what happens? Okay, so here the thing that okay, wait, sorry, 1 second. I'm having a Wi-Fi problem. Can you give me just 1 sec here?
Sure.
What we assumed here, right, or when we go back to this picture, the thing that we all assumed, or at least I was assuming, is that like, okay, let's say I'm given a data from task 2, right? Which mask should I use? I should use mask 2, right? But the problem is, how can I know that I actually, like, what if I don't know that this data is actually from task 2? What should I do? Then I don't know what mask to use at all. So this algorithm that we've described it so far is kind of only useful in this really special circumstance where we actually know which task data belongs to. So, I trained on 10 dogs, then I trained on 10 fish, and then so on and so on and so on. But now I see a fish, and I learned that 80 tasks ago. So I need to know to use this tasks ago. But what if I'm not told these are fish? So that's what sort of the rest of our discussion is going to be about. So this assumption that was implicit here was that I told you what task we were actually doing inference on, and so you told me, okay, then we have to use this mask. This is, of course, not going to be the case in real life if I'm just learning a bunch of problems sequentially, and then I just see data and I don't know which problem it's from. So does that make sense where we're going now?
Yep.
Okay, cool. So yeah, how should we do that? What we call this is the task information, so which task data belongs to, out of those 100 tasks so far, is not going to be available during inference. So we get this green data. This is actually from task 2, so we should use mask 2, but we don't know that. The task is unknown. We're not told. So what we do is we use a superposition of all masks that we've learned so far. So literally just stacking all of these masks on top of each other with uniform weighting. We're going to use a superposition of all those masks. So concretely, let's let n be the number of tasks, and let's consider this mixing coefficients alpha, so 1 over n all the way to 1 over n. Essentially what's going to happen is we're going to do now this, we're going to get the output, but now you can see this neural network is going to take in this data, and it's going to not modulate data by any particular mask, but instead modulate data, which are the network parameters, by a superposition of all masks learned so far. So alpha I, mi. And we're going to get this sort of blobby output here, which doesn't really look like the output we'd expect to see. The output that we'd expect to see, as this is sort of an image classification, is sort of logits that are particularly spiked around sort of the correct answer. But since we're kind of just using here essentially random weights, we're just stacking all these masks together, we kind of expect to see a blob like this. So we call this here the superimposed output. Now what we have to do is we actually have to sort of think about, okay, we have the superimposed output, but what we actually want to do is we want to get the mask that we actually should use and get the right outputs. And how we can do that is we can say, okay, if I train this neural network on dogs and then I show it a picture of a fish, it's going to be sort of confused. It's going to say, okay, well, I don't really know if this fish is a golden retriever or what type of dog this is, because this is a fish. You know, this doesn't look like an image I've seen. But if we show this fish to the network that was trained on the fish task, it's probably going to be pretty confident. It's going to say, okay, this is a pike. So what we're actually going to do is we're going to try to choose these alphas such that the confidence here is maximized. Since this is a probability distribution, we can also equivalently minimize entropy, and that's kind of equivalent to maximizing confidence, but entropy is sort of this differentiable thing. So what we're going to do is the following: maximize confidence with 1 step of gradient descent on these mixing coefficients alpha. So what that means is we're going to take this gradient with respect to alpha, and we're going to choose, okay, which which alpha it increases the most when we actually do this 1 step of gradient descent. And then, okay, let's actually just take the corresponding alpha, and then let's do the pass there. Now, hopefully we get something that's maximal confidence, and hopefully, this is the right thing. This is sort of a very confusing algorithm. I hope to try to explain somewhat intuitively what's going on and what's the motivations here, but please ask questions, so hopefully I can clarify things.
Yeah, so alpha is the coefficient for each mask, right? So you have n masks, you have n alphas.
Mm-hmm.
Okay, yeah.
Exactly. Okay. Are there any more questions or any parts that you would like me to go over again? Okay, then I'll continue. So basically what we're going to do now is we're going to consider the performance of this on the task of permuted MNIST. And permuted MNIST is as follows. Task 0 is just going to be regular MNIST. Now when we go to task 1, what we're going to actually do is permute all the pixels of MNIST in a fixed permutation to make a new MNIST, a new data set of MNIST that has this fixed permutation, and we're going to train. And because there's kind of like just, countless permutations, we can create as many tasks as we want. We can see what happens here, which is that our method, SupSup, actually just doesn't ever experience any performance decrease, because no matter how many tasks we've learned, with that algorithm, it's always able to sort of select this correct mask when it needs to. Now, the really interesting thing about this, and sort of here's the upper bound here in this dashed horizontal line, and the reason for this performance discrepancy is just because we're not really training the weights here. It's just this masking business. So now oh yeah, and performance is kind of a little lower than you expect on MNIST just because we're using fully connected, like we're using basically the basic LUNet thing. You can't really use a ConvNet here because we're doing permutations of the pixels. So, okay, the thing that's really striking about this figure is that these baselines that we're comparing to, which is parameter superposition and batch ensembles, we're actually allowing these to have access to task identity at inference time. So at inference time, these baselines have this sort of shortcut, which is like we tell them which task they're performing inference on. But for our method, we're not going to do that. So we're just going to show it in an MNIST image, and it has to figure out, okay, what actual permutation is this from? And given that information, invoke the right task. So now we're going to go and consider even a harder scenario, which is like, okay, what if task information is not even available during training? So I'm going to train the network on fish, the fish classification task, and then, you know, after 1,000 iterations, I'm going to switch it to dogs. Now it's training on dogs, but we're going to never tell the network that actually this switch occurred. How can we use this algorithm to solve that task? So what we're going to do is that during training, we're going to occasionally attempt to infer this task identity. Every 100 steps of training, we're going to say, okay, which task does this come from? Which task does this come from? With the same algorithm we've described before. And if we're ever uncertain, if we ever try to say, okay, we should be using mask, blah here, and we ever don't know, then what we can do is we can just allocate a new mask and continue. And here we're showing that, well, this process only starts failing. See, so soup here with an asterisk is also, so we're going to do the same permuted MNIST task, but we're not even going to tell it during training that we're doing a new permutation now. And we can see that only around 2,000 tasks does this stop sort of experience any performance decrease, whereas our soup method the soup method where we're actually going to tell it the task identity during training. So we're going to say, okay, this is permutation numbered 2001. That experiences still no accuracy loss up to that many tasks learned. So this was sort of a this is kind of like the hardest level of this problem, which is that now you don't even have task information during training.
Yeah, so I have a question about like 2 slides ago. So how does it infer like which task it is at test time, or does it know what? Yeah, this one.
Yes, so that's a good question. That's basically according to this algorithm here, so this is all happening during test time. So once it sees a new image, and what it does is it tries to pick the mask that maximizes the confidence of the outputs. So this is the idea that if it's a fish and I show it to the dog network at inference time, if I show it to the dog network's not going to be confident in its answer. It's going to say it's probably going to be pretty uniform across dogs. But if I show it to the fish network will be a little more certain. Yeah. It will say. So that's what that everything. So the key thing which I did not say is that this is all happening at inference time. And the reason that this can happen at inference time is because the objective is completely unsupervised. It's just the confidence of the outputs. So it does not make use at all of the labels.
Okay, so in these formulas, like alpha never changes.
So alpha, basically, so these mixing coefficients, we're kind of just using these. We just want to take a gradient step. Yeah, essentially alpha never. Right. Okay, so for each new image, we reset alpha to be uniform. Yes.
Okay, so I'm asking, like, out of these parameters, which ones are like learned in a sense, and which ones are like fixed?
So during inference, kind of nothing is changing. Everything is fixed during inference, but instead of doing one forwards pass, we're doing 2 forwards passes. So first we do the forwards pass with over here with the superimposed masks, so all masks. And then once we do this sort of gradient, we look at this gradient and we say, okay, it looks like mask 10 is going to really increase the confidence of our output. So now we do another forwards pass, but instead of using all of the masks like we just did, we're now only using 1 mask, and that's what we return. So nothing's changing, but we are required to do 2 forwards passes.
Okay, makes sense. Thanks.
Yeah, great question.
I had a question on the current slides. Like we were talking about the when we don't have any task identity with us, so then we need to select some threshold, right? Like when we'll say that okay, there's a new task now. So is it so that is another parameter that you need to choose, right? So how
Yeah.
did you actually choose that?
So that's a great question. Like this sort of exploration and this task information is not available during training. Is much less thorough than the rest of the work, just because it's kind of like something tacked on at the end. That's like, wow, wouldn't this be cool for future work? Let's show some initial experiments in this direction, but we're not going to go into detail here. Yes, you're absolutely right. There is a parameter that you need to tune. That's sort of this threshold. Here we're just picking this manually by seeing what works, what doesn't work. But that is a little suboptimal, and probably given a new task that's not permuted MNIST, you need some new threshold. So yeah, I definitely acknowledge that's kind of a shortcoming, and I definitely hope. Yeah.
I have a question as well. Can you go back 2 slides? To the gradient procedure items. Yeah. So I'm just wondering, how is the output of this procedure different from just taking max of the superimposed distributions?
So you're saying ignore this thing here, just do one pass here, and you get this here, and then you're just going to do the math. Oh, like, okay, because you're saying in this picture, this, okay, I understand the question. Here's why. It's because if neural networks were linear and it was just one layer, it would be exactly the same. But neural networks are nonlinear, so messing with around with things kind of earlier here is going to have cascading effects later. So it just kind of like so basically, you're absolutely right that basically because things are nonlinear, things get kind of messed up as you go deeper and deeper and deeper. So it just is a little different. Like sort of, you can think about the value of these neurons here is different than the value that these neurons here are going to see, and because of it's not sort of just a direct superposition anymore, because of these neural network nonlinearities.
I see. So does this also acts like a calibrator? Like at the end, it calibrates the score so that now the max is actually the max.
Yes. Let's see. Calibrator. So do you mind, sorry, I'm not really sure what you mean by that. Do you mind explaining?
Is it also possible that in the first case where the max does not correspond to the correct class is because the output of these marks are not calibrated and the scores are not calibrated?
I see with each other.
Makes them calibrated so that then you can just simply take the max.
I see. That's a very good point. The answer is I don't know. I see what you mean. So if these things work, basically my intuition is that because of these nonlinearities, you're kind of still out of luck here, and you have to do this two-step thing. But honestly, I don't know. If you actually just make these calibrated, it could just work. So I'm not sure. But yeah, great question.
Thanks.
Yeah, and this is explained in more detail in the paper if hopefully well, but yeah. Oh, okay. Now we're going to go on to part 2, which is subspaces. So we talked about subnetworks, and now we're going to talk about subspaces. And hopefully this part of the talk is a little bit more better, just because I've talked about this more recently and done this work more recently. So yeah, that's the hope. We'll see what happens. Okay, so basically what we're going to do is first review some key observations about what's called the lost landscape. And then we're going to talk about, okay, what is a neural network subspace, and sort of like why and how should we actually be considering learning these things, and then kind of like, well, okay, what's next? What are we going to do with these concepts going forward? So first, have people heard about the lost landscape at all? I'm not really sure how common this is a thing of like people talking about when they talk about neural networks.
I've heard of it, but not really familiar with it.
Okay, cool. So we'll explain basically everything we need to know. Essentially, what the loss landscape is kind of, you can think about training as you start with some initial parameters which are random. So the network's going to achieve kind of like a very high error, very high loss. And as we train, what we're going to be doing is just kind of following gravity, almost like the gradient, and we're going to be hoping to end up in a region here that has a much lower loss. And that's basically the loss landscape just says like, okay, we can conceptualize training as movement in some vast loss landscape, which is kind of this mountainous region where these mountain peaks consist of really high error, high loss points. And as we train, we just kind of like follow gravity, and we're going to go down and down and down until we get to a region of low loss. And this is kind of like a schematic for like what this picture might look like. This is what we hope training looks like. Is that sort of makes sense? How like we can think about these neural network parameters are just kind of these like vectors in Rn. So these points in Rn, or I guess I'm using D here. We can think about these parameters as kind of like a point in D dimensions, and we're just going to move this through this D-dimensional landscape and hopefully end up in a region of low error. Does that make sense? Or are there any more questions before we proceed about that? I guess this is sort of how I learned SGD when I learned about it. Like someone just like said, oh, you're like rolling down a hill, and that hill is just the loss landscape is kind of the short answer here. Okay, so let's proceed. We're going to talk about some sort of observations that people have made about the loss landscape. The first is that if we train twice with two different random seeds, we're going to end up in two different basins. And so actually, but what we can actually do is when we end up in these two different basins, what we can do is we can actually ensemble the two networks together. So not just do sort of one pass here. So here again, X is data, theta is parameters. We can actually do first a pass through with parameters theta 1, then a pass with parameters theta 2, and then let's actually just ensemble, which basically just means add their outputs. And this is actually going to vastly improve accuracy because these two basins correspond to two different ways of solving this problem, which is pretty interesting. Like these two neural networks are going to make somewhat uncorrelated errors, and they're going to actually correct each other's mistakes when we ensemble them. So that's observation. Yes.
Yeah, I have a quick question. So this doesn't necessarily mean that the ensembles are mode connected, right?
No, great questions. It does not mean anything about mode. Yeah, it does not. All it says is that when we train twice with two different random seeds, we're not ending up in the same place. And when we don't end up in the same place, if we just ensemble these two neural networks together, it's going to do well. But we're going to start talking about mode connectivity right now. So yeah. So observation 2. Oh yeah.
Sorry, I had yeah. So you're ensembling in the output space. So I assume that means we don't necessarily have parameters in the weight space corresponding to the ensemble.
That's right.
Okay, thanks.
So observation 2 is gonna do that. It's gonna say, let's consider a line between these two neural networks, and let's sort of go to this point halfway through the line, and let's consider the parameters which are over there. So let's ensemble in weight space and see what happens. And from the schematic, we can already see what happens is this fails. This completely fails. It performs no better than random chance. The neural network, which the parameters, which are kind of just an average of these two parameters, don't do anything. There's this high barrier on the linear path between these two networks. So observation 3, okay, yeah.
What was the intuition even having a linear connectivity and assuming that halfway through this connection you'll obtain a set of weight metrics that will perform well? Like what was the motivation to do that in the first place?
By Franco at all?
Yeah.
You'll see.
Okay.
So observation 3 is this kind of surprising finding that says, okay, although the linear path is not a mode connector, there does exist a nonlinear path in weight space between the two solutions along which loss remains low. So although it's not this straight line, I can follow this kind of curvy path, and I can get from theta 1 to theta 2 on a path where error is going to remain low the whole time. So now we're going to talk about kind of like why was Frankel even doing this? And it's because of observation 4, which says that if I train for k epochs, and then I consider two different, then I sort of fork off and consider two different trainings with two different random noise. So here, this is kind of the same trajectory. And then at epoch k, I'm going to split off now and train twice. What does happen is that there is linear mode connectivity here. I guess one of these thetas has disappeared, but imagine theta 1 t is here. So does this make sense that like, okay, or not make sense? I mean, none of this makes sense, but does this observation make sense in the context of observation 2? It says that, okay, if I actually if I train twice. Oh, sorry, actually, I skipped one of these, which just says like nothing changes if I consider sort of a shared initialization or I consider two different initializations. But so if I train twice with two different random seeds, I end up here, linear mode connectivity completely fails. But if I train for part of the trajectory shared and then I split off, then I do end up in this linear mode connected region. I end up in the same basin, and yes, and I actually so the real motivation for Frankel's work here actually goes back to lottery tickets, and I really recommend reading this paper to see the connection between this and lottery tickets, which is really cool. But anyways, this is kind of the idea, and like k is very small. So for ImageNet, for example, you can set k to be 20 epochs. So you train for 20 epochs, now you train for a remaining 80 epochs separately, and you still end up in the same basin. So this is pretty cool. There's one more observation that we're going to talk about here. Oh yeah, and like please interrupt me if things aren't making sense or just in general for feedback, because I know like this is a lot of information.
Yeah, just one quick question out of curiosity. Do you know if like the basins that they end up in are the same if you train for say like 20 epochs versus say like 120 epochs?
No, I do not know.
Because they're both linear, right?
Yes, I have no idea. Do not know. I mean, hopefully we'll learn more about these basins today, but we will not learn that because I don't know.
I had a question too. So when you say split off, like after k epochs, like what exactly does that mean? So just injecting noise into the gradients, or?
No. So actually, what we're gonna do is, or what Frankel's gonna do is, consider like a epoch like 21. Okay, now this is the first epoch where they're different. Just shuffle one of the datas twice, so different data order, and that's going to simulate different sort of SGD noise.
Okay, I see.
Yeah. Okay, cool. This is a final observation, so don't worry. I know this is a lot of context here, but final observation says that weights found through SGD tend to lie at the periphery of kind of large flat space. You can imagine kind of like this big lake. When we train with SGD, we're going to just go right to the lake's surface. But sort of the lake keeps going down under the surface. It goes to a very, very low point. We just can't really see that because we're only looking at the train loss. We're not looking at the test loss. So where we actually want to be is right at the center of the lake. So how we can get there? If we only see the lake, how can we actually go to the middle of the lake? There's this really neat algorithm to do that called stochastic weight averaging by Ismailov et al., which says that I'm going to train, and now I'm going to save a checkpoint here at epoch 75. Now I'm going to save one at epoch 80. Now I'm going to save one at epoch 85. Now I'm going to save one at epoch 90, and I'm just going to average all of these together. And what's happening is that here I'm kind of bouncing around this lake, and now when I average these together, I'm going to go closer to the center of the lake. That's observation 5. And so let's recap. It says that observation 1 told us that high accuracy subspaces contain models which are functionally diverse and may be ensembled in output space for improved performance. That was observation 1. Moreover, taking the midpoint of a subspace this was observation 1 and 3 because the subspace, so here we're using subspace to consider to mean kind of this like big connected region of low loss. So we saw that high accuracy subspaces contained models which are functionally diverse and they can be ensembled in output space. So basically, like, you know, this was a big subspace here, and it had two solutions in it, which were functionally diverse, and I could take both of those, and that's useful because now we can get a much better neural network. And now observation 2 says, like, okay, also subspaces are nice because if I just take the midpoint of a subspace, I can actually get a network that's like maybe generalizes better, and that's observation 5. So here's the problem. It's that prior work satisfying 1 requires multiple training runs, while subspaces satisfying 2 are less functionally diverse. So what that means is that here, when I found these two sets of weights, I actually had to train twice, and that's expensive to do. It's also expensive if we think, well, these are just part of the same thing. So is there a way to actually do this without actually training twice? And the problem too is that if I actually just consider these checkpoints and I ensemble them together, they're not as diverse. They're just because these are kind of like closer together than those other ones, just because they're part of the same optimization trajectory. These have like sort of less. This is kind of the weight space ensemble. Okay, this works good, but the output space ensemble provides less benefits. So now we're going to talk about learning neural network subspaces, which just says that, okay, instead of actually considering a single point and moving this point through the optimization trajectory, let's actually consider a line of neural networks. So let's consider this initialization 1, initialization 2, and now let's consider kind of the path which connects them. So the linear interpolation between these two randomly initialized neural networks.
I have a question in the previous slide. Previous to previous, the one before this. Yeah.
This one?
Yeah. So here you're saying that you have this very big, flat, wide minima, where at the center you have the optimal point and you want to sort of reach that. And you take these n steps and checkpoint each step and sort of average them. How does this approximate that center point? And also assuming that there is a gradient process involved, the whole red lake in between has very, very low gradients, right? So how would you average it or reach that point even?
Yeah, so the fact that there is no gradient signal here is why they have to do this trick where they're taking these things at the edge of the lake and just sort of averaging these weights together, because you actually, like, gradients will never tell you how to move here because it's like you get no signal. In terms of your first, so does that answer kind of your second question of like, how do you deal with the fact that there's no gradients? Can you restate your first question slightly?
Yeah, the first question was, how does this averaging sort of approximate that center point if that's the goal?
Oh, I see. Like, okay, how close does this get to actually like the true basin center? I have no idea. I think the way to do that would be to actually like just train on the test data, see where you end up. That's a really good question. I don't know how well it approximates the true average. But,
and also for this to work, they must be using not a LRDK, but increasing the learning rate to skip out.
That's a really good question. They're using a constant learning rate here. Yeah, sorry. Yeah. You're exactly right. They're using sort of a learning rate. They're decaying it during this part, but then it just stays the same. And they also have another variant where they use cyclic learning rate decay, but so like decreases and then decreases and then so forth. Yeah, that's right. That's right.
And what is is there any optimal number of checkpoints that they take? And also how is the checkpoint even decided, the first checkpoint even?
I would recommend reading Ismailov et al. 2018 for more information, because I don't want to misrepresent their work because I don't have all these answers off the top of my head. But it's a very nice paper.
Right. Okay.
So what we're going to do is we're going to consider one neural network over here, one neural network over here, just two randomly initialized neural networks. We're going to consider the line which span between them. And now instead of kind of moving a single point through this lost landscape, we're going to move this entire subspace through this lost landscape. So we're going to get this point over here, and we're going to get this line of neural networks which performs well. Why? Well, hopefully the endpoints here are going to actually enable high accuracy ensembles in a single training run. while the midpoint is going to be right at the base and center and actually outperform standard training. This is like our hope. This is sort of the schematic of how we wish to proceed in our algorithm, and this is the schematic of like what we hope happens. Does this sort of make sense as a goal? Or are people like, what does it mean to consider a line? Like, well, what's any questions?
Makes sense.
Okay, cool. So great. Let's proceed. Yeah, that's why I like presenting the observations first, just because I feel like this now makes sense in the context of all those things. But you know, everything's like that. Okay, so how are we going to do this? It's a learning algorithm which resembles another algorithm, but we're going to sort of apply it differently here. So for each batch XY, what we're going to do is we're going to say, let's consider a random set of weights along this line. So these endpoints here, these are the learned parameters. And so what we're going to do is, for each batch, we're going to sample an alpha, which is a random alpha in 0, 1. And we're going to say, okay, now we're going to go, we're going to interpolate with coefficient alpha to get here these green sets of weights. What we're going to do is we're going to do the forwards and backwards pass with those green sets of weights. And then what we're going to do is just, okay, since this whole process was differentiable, we can just backprop to learn the endpoints. So essentially the algorithm is as follows. For each batch, consider a random point on the line, go there, do the forwards and backwards pass, and backprop through the endpoints, because look, like this here is differentiable. So, you know, you can imagine if you just wrote this in PyTorch or TensorFlow, you can just backprop right through that, and you're going to get gradients to theta A and theta B. So that's sort of the very simple algorithm. But you'll notice that in addition to this loss term here, we have this dist term, which is the distance between theta A and theta B. And this is something that we want to be increasing. So now we're going to look at kind of like the forces which act to form this subspace. And they're as follows. We get these train loss gradients shown in blue. We're going to first get it to the green point, and then we're going to distribute it to both of the endpoints. But then we're also going to have a momentum term here, theta A, theta B, and we're going to have a regularization term here, which is going to try to stretch out this subspace. And that is the algorithm. And yes.
I have a question. So there has been a lot of works that sort of approximate the weight space in different types of metric spaces. So what is the metric space over here? You're just considering just like by distance, what is the type of distance that you're computing?
Oh, great question. That is the next slide. Let's talk about that. So what type of distance do we want to consider here? And so, but is everyone clear with kind of like, okay, how are we going to like make this subspace essentially like shape this? Okay, so yeah, I'll talk about what distance. Sorry, go ahead.
Another quick question. What's the motivation behind trying to make the distance between them large?
Oh, good question. Because what we really want is that the endpoints here are going to be neural networks that we want to, like we want to get these two neural networks which are far apart and we can ensemble in a single, we want to train once and get two neural networks which we can ensemble together for boosted performance. But you can think about if this line is very, very, very tiny, then those neural networks will be much closer to each other.
I see. Yeah. Okay. Thank you.
So are you talking about the diversity of the networks that you are learning? Like the diversity
right. So I'm kind of doing something here which is illegal, which is that I'm assuming that neural networks which are far apart are going to be functionally diverse, and that's not really correct. But when we start talking about this distance metric, maybe you'll start believing me that like this distance is going to correlate with functional diversity.
And like here we are talking about the convex combination of these 2 points, right? Like we are talking about a vector here, right?
Yes.
Okay.
So then we're going to talk about this distance. Well, okay. Basically, the idea is like, what does distance mean? We want some distance metric which is going to promote functional diversity. But of course, we don't want to actually like do the forwards pass for both of the endpoints because that's going to be expensive. So the first distance we were thinking about is like, okay, L2 distance between the endpoints. But this is actually a bad idea because we can arbitrarily scale up all the parameters in the network, and it's still going to compute the same thing because of like normalization, like group norm and batch norm, whatever. So essentially, the distance metric that we end up using is cosine distance. So what we're going to do is we're going to try to make these endpoints orthogonal. And if these if all the network weights in the networks are orthogonal, we're going to say, okay, probably they're not computing the same thing. So that's going to be the distance that we want. And, it's somewhat motivated by the fact that if we actually just train twice, we're also going to end up with orthogonal wave vectors, just because like most random, random points in high dimensions just happen to be orthogonal. Yeah, that's what's going on here. Do I think that this distance metric is the best distance metric? No way. I think that someone is gonna, someone can come up with a better one if they know more than us. This was just kind of what we tried. Yeah. So we're sort of like, we're not limited to lines in this investigation, right? Nothing really ever was central to lines. We can go back and look at this algorithm, and instead of doing sample a random point on this line, we can just do sample a random point on this subspace. So we can train all sorts of other shapes from scratch. So in addition to considering like training lines from scratch, we can consider training curves from scratch. We can consider learning simplexes from scratch, which are, yeah. And like we can just train these things. So we can consider like a simplex of like 8 points, like the convex hull of these 8 randomly initialized neural networks, and just move this entire thing to be the lost landscape, which is pretty fun. So let's look at like what happens. Here we're going to train this curve, and they're like, oh, okay, it looks like a curve. You'll notice like a curve is parameterized by 3 points. It's just a quadratic Bezier curve here. It doesn't actually pass through this point. It just like, this point is used to like kind of construct the curve, but it never passes through. So this is the actual curve that we've learned. Here we've learned a 2 simplex, which is like a triangle. Here we've learned a line, and since we're considering here, there's like kind of like 2D slice of the lost landscape. To draw to plot this, we just trained a third neural network, and now we're just considering kind of like what this looks like. So you can see like there's this huge high area barrier between these two things, but this one's kind of right on the periphery of this minimum here, and like yeah. So and you'll also notice like this is I love this example because like you can see that here in the middle of this lake, we're actually getting this like high, this better thing than we actually got when we did standard training. Anyways. So I'm actually going to... Yeah.
I didn't really understand that third neural network.
Basically, this star here is just the third, like, so we trained this line, and then we just trained another neural network. So this is the other neural network over here, and this is the line. So these are not related in any way. It's just this, we just needed kind of like a third point to make this 2D slice plot.
Right. And could you go back just one more slide?
Sorry?
Could you go back one previous slide? Yeah, so in that curve, is that the third star is also representing the...
No, so basically like, okay, to make this 2D slice plots, you need 3 points, just because, between any 2 points is a line, between any 3 points is a plane. Right. So these each had, the curve and the 2 simplex each had 3 endpoints. So see the curve has this theta 1, theta 2, theta 3. This can have, if this was this is a 4 simplex, but if this was a 2 simplex, it would just have theta 1, theta 2, theta 3. So for these, we could just automatically make these slice diagrams. This just has theta 1, theta 2. So we need some theta 3 over here to do the slice. So for the line, we just are going to, just for the sake of visualization, just train a third theta 3 and just make the plot.
Got it. Thanks. Yeah.
Let's skip through this stuff. Okay, let's look at accuracy along these subspaces. So like, how does accuracy differ along these subspaces? So here is actually standard training. And then we can say that as we're going from alpha equals 0, so the left endpoint to alpha equals 1, right endpoint of the curve or the line, accuracy is going to be like above this horizontal line, or matches or exceeds the accuracy of standard training for like a large portion of the subspace, which is really cool. So instead of just getting one point, which got, like whatever this is, tiny ImageNet 68 on tiny ImageNet. Now we get these like a whole range of points, which is all getting this accuracy, which is really nice. And so the lower horizontal line is kind of standard training, and this upper horizontal line here is the standard ensemble of 2. So what we really want to know is, like, can we actually match this? If we take 2 networks from this subspace and then we ensemble them, like, does this actually look like a standard ensemble? And the answer is, like, yes. In this case, we actually do have 2 points from this subspace that we found in one training run, such that when we ensemble them, we can match the accuracy of the match ensemble accuracy. So that's pretty nice, because this was kind of our goal here. And we also see, like, slightly interesting thing is that, like, curves are not really getting us much more than a line here, which a priori I thought, like, okay, these curves are going to bias way more in terms of, like, getting neural networks which are functionally diverse. But actually, like, no, I don't think that's the case anymore, because the lines are so close to curves here. Okay, this is kind of like the main result. So are there any questions about this? Because this is kind of the one result I would like to convey.
So go ahead.
Okay, so I just wanted to ask something more from an initialization perspective. Did you? I've read some works on orthogonal initialization and how they improve rate of convergence and propagate isometry. Have you tried this out with various types of initialization, and whether there is any interesting pattern or trend that goes on?
No, so basically, like, these, when we do this, and we're like, all these points are just like literally, this is just like torch NN random uniform whatever, and then this one is just like torch NN random uniform. Like, all of these points are just like default PyTorch initialization, and then you just consider this line between them. So, like, totally, this is not the best way to initialize a line. Like, this doesn't actually, like, this is super unprincipled, and like, but I mean, that sort of, to me, is part of the fun here. It's just like this idea that these loss landscapes are very benign, they allow you to do sort of like really whatever you want.
Right. Okay.
Was there another question?
Yeah, I had a quick one. So the fact that you mentioned that lines perform just as well as curves is kind of surprising. Did you observe the same thing for, like, higher dimensional, or like the simplexes and all that?
Oh, good question. Simplexes. So what happens with simplexes? Let's go here. Okay, this is yeah. So basically, what happens with simplexes is that simplexes stop because once you consider these really high dimensional simplexes, these spaces are just so big that accuracy is gonna fall off near the endpoints. Because you can think about, like, when you're sampling during training, you're going to actually, like, cover a one-dimensional curve or a one-dimensional line pretty well. But once you start talking about four-dimensional simplexes, you're not really going to cover this whole thing that well. So probably my guess is, like, you'd really have to train these simplexes for longer if you wanted to get, like, really consistent accuracy across the whole simplex. But what are simplexes really good for? Simplexes are really good for taking the midpoint, and then that midpoint is going to perform really well. So if I train like an 8-dimensional simplex, and I take the midpoint of that simplex, because I've sort of enforced that there's high accuracy everywhere around that midpoint is going to be sort of that center of the lake thing that we were going to talk about. So that's what we see kind of as we go along here. So if we look at ResNet 18 tiny ImageNet, number of endpoints as we go from, like, 2, which is the line, all the way to 10 here, or 11 or something. So the stochastic weight averaging improves, and it gets, like, a nice boost over standard training. But these simplexes keep going up in accuracy as we sort of these simplexes, the midpoint of these simplexes keeps boosting in accuracy. There's this thing here called layer-wise, and we haven't talked about this, but it's basically like a trick to sample more points from the subspace as you're going. And what it just means is that instead of sampling one alpha for the whole entire network, like globally, you're going to sort of do a different point on the subspace. You're going to consider a subspace for each layer, and you're going to pick a different point on the subspace for each layer.
Yeah, I have another question.
Yes.
Sorry, go ahead.
Oh, yeah. So, but do you think the assumption about having a more diversity by maximizing the distance, or including the distance in the last term holds for higher dimensional structures, like, or is there any way to sort of normalize that in some sense, where if you increase the dimensionality of the sort of the set that you're the set of weights, is that?
I don't. That's a great question. I'm not sure. We're not doing anything special for higher dimensions there, but you could.
Okay.
Yeah. No. I'm not sure. Now, like, basically, if I'm going to convey anything here, it's that the lost landscape is like really unexplored, and we don't actually know much about what's going on there. So, like, I really think that understanding that better is going to be really a key to improving neural networks. And there's a lot of really fantastic people that are doing interesting work there, and I really encourage you to check it out.
Okay. Yeah.
Okay, like this is kind of the main point that I wanted to convey. There's kind of some other things, but I think maybe so that we can talk either. I think if we have 20 more minutes left, we can have some just like open-ended discussion, or I can tell you a bit about where we're going next with all this. So which do people prefer?
You can. I mean, I would like to know more about where we're going ahead with this.
Okay. So let's talk about that a little bit briefly. So where we are going next, which hopefully this is a paper that will get out next week or something. But essentially, here's the main idea of what we're going to actually do with this. So we said about this kind of like flatness idea, right? What does this what does this mean? Like if we kind of like step back and consider things like really abstractly here, it means that there's lots of room to move around while accuracy is, or it's like there's lots of room to move around without decreasing loss on my problem. So if it's ImageNet, I can really like move around a lot while still having like pretty good ImageNet accuracy. And like that's kind of like interesting because, well, like what's happening when I'm moving around? Like clearly what's happening isn't going to influence anything about how I'm predicting ImageNet. Well, so what is it doing? And like in the informal answer here, which is maybe not correct, but this is kind of like the intuition is that movement will maybe corresponds to different explanations of what's not in the data set. So movement in this region won't affect how I'm doing on ImageNet, but maybe it will affect how I'm doing on sketches of ImageNet. So that's sort of like where we're going next at a high level. So can we find more robust solutions by just like looking around here? That's kind of like the next steps are like and I'll send basically when we have the preprint up our paper, which is going to be talking about that idea. Are there any questions there?
So when you say, can we find more robust solutions if we just traverse that space over there, what's the intuition behind that? Like, do you expect, like, for example, if you take like two minimas which are more connected to, I'm not sure, I've not followed the literature, but do they, like, if they have the same laws, do they have different robustness as well, or do they have the same robustness as well?
That's a very good question. So what we're going to do, or we're trying to do, is we're going to get one point over here which performs well on in distribution, and we're going to get one point over here which performs well, okay, maybe it's going to be over here, which performs well out of distribution. And we're going to just traverse here the path spanned by these two networks. And we're going to say, hopefully in the middle, there's going to be a point that performs good both in and out of distribution.
Oh, okay. So just to reiterate, so you have network theta 0 that you're training on, let's say C410, and then you have a network theta 1 that you're training on, let's say ISIN, and you basically say that the second one is OD, first one is ID, and you try to approximate a midpoint between the connection of two networks in the weight space, right?
Essentially, yes. And there's an additional trick that you have to make sure that these things like don't leave the same region. Like you have to make sure that like the weight space ensemble still does good. But yes, that's the main idea. That's exactly it. Yeah.
So like here we're talking about robust solutions. So robust to what exactly?
Distribution shift. So essentially what we want is that if we have a network which performs well on ImageNet, and then we show it sketches of ImageNet. So ImageNet sketch, it's called, it's a data set of like that's like ImageNet, but it's just sketches. We want to say, okay, accuracy on ImageNet should be, close. We should probably expect some drop when we go see sketches. But if we see like, okay, we're getting 80% on ImageNet, then 40% on the sketches of ImageNet, that's not robust. But if we see 80% on ImageNet and then 60% on ImageNet sketch, like, okay, that's more robust than the other one. And we plan to have, yeah. So that's robustness to distribution shift. And we'll have more discussion on that on the paper, which, is mostly going to just be references to really great work that's sort of talked about this before. I really recommend the paper Do ImageNet Classifiers Generalized to ImageNet. That is a really nice paper, which definitely got like taught me a lot about these things. So, yeah.
Isn't the idea of finding this solution you're talking about very similar to the whole idea of elastic weight regularization as well?
EWC, yes. EWC, so that one is going to be okay. So yes, it is similar to EWC. Let me think about this for 1 second. EWC is going to try to find a point which performs well on both solutions. Yes, it is very similar to EWC. The difference here is that EWC would need to actually do training out of distribution. EWC, if applied to this task, would say we're going to train on one in distribution task, and then we're going to train on one out of distribution task. And that's kind of like the motivation that I was also saying that we were going to do. But of course, you actually can't do that. You can't really train on out of distribution in real life. So what we're going to do is we're going to actually try to get something that performs good out of distribution, and then get something that performs well in distribution. But we're not actually going to train on the out of distribution things. So what we're actually going to do so if we were actually training on the out of distribution things, then yes, this would be like pretty much exactly EWC. But what we're going to actually do is we're going to take clip zero-shot models. Clip zero-shot models are very, very robust to distribution shift. These perform very well out of distribution. The problem is that these don't perform, state-of-the-art in distribution. Even though they perform really, really well out of distribution, their in distribution performance is only like around ResNet 50. So can we actually get the best of both worlds here? Can we have a model that's like 85 on ImageNet, but also really robust out of distribution? And so that's kind of like where what we're thinking about next. And I'll circulate the preprint, which is hopefully available soon and can express these ideas a little more concretely.
Interesting. Yeah, that's pretty cool. I look forward to the paper. And do you mind also sharing the slides later after this call, so that we can share it with everyone?
Yes. Can I have? So I'm currently traveling. Do you mind if I just do that after I'm back from traveling?
Yeah, sure. Absolutely.
Okay, cool. Yeah. No, I mean, thank you so much for having me. I really enjoyed talking with you all today, and thanks so much for taking the time. And hopefully some of these ideas are somewhat fun to talk about. And yeah.
Yeah, that sounds cool. I believe Ajay was the only person who didn't have a chance to introduce himself. So Ajay, if you want to quickly introduce yourself, that would be pretty good.
Oh, Yeah, sure. I'm Ajay. I'm a student at the University of Illinois at Urbana-Champaign. Things I'm broadly interested in, deep learning of all kinds, but primarily NLP, I guess. Ray tracing and compilers also, I guess, sort of the intersection of all those things. So yeah.
Cool. Yeah, it was so nice to meet all of you today. Yeah, thanks so much, and thanks for the great questions as well.
Great. I guess we don't have any more questions. So if not, we can conclude here. And yeah, I want to thank Mitchell again for taking your time out to do this presentation today. A lot of people were quite excited, especially for your neural network subspaces work. And yeah, I personally really enjoyed it. I hope others did as well. And as I said, we were live streaming this, so if anyone did join in, I hope we can get some feedback on how it went. But yeah, we hope to have you sometime in the future for your future works as well, and look forward to staying in touch.
Yeah, thank you so much.
All right,
See you,
I'll see you
everyone.
around.
Yep.
Bye-bye.
Thank you.
Thanks. Yep.
Thanks.
Bye.
Bye.
Are we still live streaming?